parabolic PDEs. Okay, so the example we looked at was the 1D heat conduction equation. The equations were alpha d square t dx square is d t d time. And then I said, because of the nature of the equation, you need one IC. So that would be t x0 is some function of x. Okay, so initially at time t equals 0, that is, the rod has some temperature profile T, and then two boundary conditions. You could be T A T equals T A T B T equals TB. This is basically saying that at x equals a, the temperature is always T of A, x equals B is TB. This is probably best illustrated if I just draw a rod here like this. So let's say that this is x equals A, this is x equals B. The temperature here is T of A, here it's T of B, and it remains T of A, T of B at any point of time. Just imagine you're heating up these ends and you're just subjecting them to some temperature. That temperature stays like that. And usually there's some temperature profile along this. That's the first one. And then you need to basically solve. The goal is to compute T as a function of x and time. So what is the temperature of this rod as time evolves? That's the second variable. And also as a function of the distance along the rod. Okay, so how do we solve this? Well, what we do is we just use finite difference. So here's the numerical solution. Now, unlike ODE, this is really hard because this one, it's very hard to guess initial conditions. So most of the PDEs you rely on using numerical methods to solve them. There is no analytical solutions for most of these problems. So what we do is we take that equation, let's give it a name. Let's call it maybe 1. And so we use finite difference on 1. So alpha, now we have d square t dx square. So I can just use the second order finite difference. I'll use the central difference. So here this thing is there's two indices, and I'm going to take care of both of them by using two indices for t, j plus 1 ij 1 divided by delta x squared. So what is Tij? Tij, here what we'll do is the first index will be used to denote time, and the second index will be used to denote position. So when you see here, it's basically finite difference on x. So it's finite difference on position, the second index, and that's why you see the second index changing. It's j plus 1, j, and j minus 1. So that's the central difference for the position index. Okay, that's the left side. On the right side, we have dt by d capital T divided by d small t. And so what we need to do there is we're just going to use forward difference for that. So that will be ti plus 1 comma j minus ti comma j divided by delta t. So here you can note that I have done the finite difference over the first index, which is the time index, because the denominator is time. And here, if you see, it was the second index. Okay, let's just carry this forward. There's an easy way of visualizing this. This seems a little hard, right? Let's see how to visualize this. Okay, for some people, this might be one way they can understand what's going on here. Okay, so if you have the x-axis and the y-axis, with the x-axis being the position, so start with 0, you just keep doing 1, 2, 3, 4. Somewhere you reach j minus 1, j, and j plus 1. Similarly, we'll use the time index on the y-axis. So you go 1, 2, 3, 4 all the way. Some point of time you reach I plus 1. That should be enough. I and I plus 1. Okay, now let's write what the combination is. It's here. Okay, so this one is ti comma j minus 1. This is ti comma j. This is ti comma j plus 1. How did I get it? I look at the ith index. That's the first one. J minus 1 comes from the position index. Here we can write ti plus 1 j minus 1, ti plus 1 j, and ti plus 1 j plus 1. Okay, so in this formula, we have t. Before we use that, let's just simplify this. This can be rewritten as follows. Okay, I'm going to skip a few steps. Just write this answer, ti plus 1 j. So I'm just trying to solve for ti plus 1 j, noting that tij is a tij here, so I can club them together. And there is tij plus 1, tij minus 1. So I can club them all together and get this formula. F tij plus 1 plus tij minus 1 plus 1 minus 2 times f tij, where f is alpha delta t divided by delta x squared. So this is simplify, right? This is I wouldn't spend time on doing that, but just you can move things around. So coming to this equation here, we are trying to solve for this. This is the temperature at time I plus 1 at index states. This is basically this point. Then we have the following things. We have ij plus 1, ij minus 1, ij. These are here. Right? So in order to compute this quantity, which is what is the temperature at time I plus 1, I need to look at the neighbors in this fashion. I need to go one level down, that is at a time index I, and look at these neighbors, these 3 neighbors, and sum them up in that fashion. And then I have ti plus 1j. Okay. Then I need to do the same thing for this one. It will be the three neighbors here, here, and the one over here. And we just have to proceed that way from bottom to top. I need to do it for I plus 1, I plus 2, I plus 3 till I get it to whatever time I need to compute the temperature. These are two things about this method. There's something called a truncation error, which we've talked about. Truncation error. It turns out the truncation error is order delta t because we used first order finite difference and then O delta x square because of delta x. So it's the sum of the two. It's actually will be the worst case. If we choose 0.1 for delta x and 0.25 for delta t, then clearly 0.25 is going to be your the one which is going to be the higher value, and that is going to will dictate the truncation error. So worst case would be the bigger the value delta between delta t and delta x will dictate the order of the error. So that's the first thing. The other thing is this method, this particular method has a stability problem. So the method is stable as long as this quantity f, which is alpha delta t delta x square, is less than half. Here the half probably comes because of this. Probably comes because of this. If you try to take greater than half, I think this term will basically blow all the way. And then you'll get you'll get solutions which go to infinity when actually the heat cannot go to infinity in the physical example. So this is the drawback of the method. It is not stable. It's conditionally stable. So in order to avoid this issue, there is another method, what is known as an implicit method, which is computationally more challenging than this method, but has no stability issues. So to overcome this, we use or to improve stability, an implicit method may be used. Okay, so the method basically relies on using a backward difference instead of forward difference. So let's see what it does. So the original equation is alpha d square t dx square equals dt d caps t d small t. What you do is you write this as ti plus 1 j I plus 1 j plus 1 minus 2ti plus 1 j plus ti plus 1 j minus 1 divided by delta x square is ti plus 1 j minus ti j divided by delta t. So what is done here is look at this. Here we've used I plus 1. Okay, this is different from what we did previously. You see, this was just I, and I. So we just change it to I plus 1. Okay, so this will give me, so if you simplify this, simplify this equation to get minus f ti plus 1 j plus 1 plus 1 plus 2f I plus 1 j minus fi times ti plus 1 j minus 1 equals tij. Okay, the problem with this method, well, not a problem, but the challenging aspect of this method is that you typically know what this value is because it's the temperature at ij, and you're typically asked to find what is the temperature at the new time profile. But you cannot solve for 3 unknowns using one equation. That's one equation, but 3 unknowns. So what you need to do is you need to assemble this for the entire time I plus 1. That will give you 3 equations, and those 3 equations will lead to, well, be 3 simultaneous equations in 3 unknowns, and so you solve for those 3 unknowns based on those 3 equations. That's why this is called an implicit method, because you don't directly get the solutions, but you get them by solving another set of equations. So that's why it is more complex, but it is guaranteed to be stable. So if you thought that was difficult to understand what I said, it will become clear when I do an example problem in the class. Okay. Now, sometimes to get the best of the 2 worlds, the best of both worlds, that is the fully implicit, this is an implicit equation, and then the explicit equation, which was this one. This is a explicit equation, explicit and implicit. What you can do is you can actually tune you have a weighting parameter and you can tune them. So dt dx square is approximated as gamma, or let's say it's gamma ti plus 1 j plus 1 minus 2 ti plus 1 j plus ti plus 1 j minus 1 divided by delta x square okay, plus you do 1 minus gamma ti j plus 1 minus 2 ti j plus ti j minus 1 divided by delta x squared. So we have a tuning parameter here, and that tuning parameter is gamma. The tuning parameter, if you put gamma equal to 0, effectively this term will be 0. You get the explicit scheme. If you put gamma equals 1, which will basically cancel off this term, because there's 1 minus gamma, you'll get the implicit scheme. This is harder to solve, but unconditionally stable. Okay, this explicit scheme is actually known as FTCS. FTCS means forward time central space. Forward time central space. This scheme, which is purely implicit, has a name. It's called Lassonen method, LAA. Seems like Swedish. And then if gamma equals half, then we have the method is known as Crank-Nicolson method. And I'll give you actually a summary of all the three methods, so you can just use them when you are solving a problem. Formulas are correct. Okay, so those are the three. Well, also F, if you remember, it's alpha delta t divided by delta x squared. Okay, so let's see how to apply these. I don't think I'll get too far in the problem, but let's get started. Three minutes left. Okay, I'm just going to set some things up which are common to both problems, and then it's just a matter of trying to use the equations which we derived. Okay, so so this is for both problem. This is true. So F is alpha delta t divided by delta x squared. So 0.2, delta t is 0.1, 0.25 square, comes out to be 0.32, which is less than half for FTCS, right? For FTCS to be stable, it should be less than half, and this is satisfied by the given capital F. Okay, we're going to use Tij. I is time index, and J is the position index. Okay, so let's look at the time. We want to use delta Ti, where I would be 0, 1, 2, 3, 4, 5. Effectively, it'll give us 0, 0.1, 0.2, 0.3, 0.4, 0.5. Right? We need to stop at 0.5. Yes. Okay, this. Okay. And then for xi, we need to go delta x times I, where I will go 0, 1, 2, 3, 0.4, I think. So let's see, sorry, this will be, my bad, this will be xj. So xj, so this is Ti, xj will be 0, 0.25, 0.5, 0.75, and 1. So this is, remember, it's I comma j. I is time. So I does not change. So this should be I. Right? The first index is time. So that time, it's true for any time. So I just put I. But then for position of 0, I should be able to write in terms of I. So position of 0, which will be the index j, that will be when I equals 0, I get 0. So this will be 0. And then for position index 1, so that's 1 here, corresponds to j equals 4. So I'll write 4. So let me write the reasoning there. X equals 0 corresponds to, I wrote this I, this should be j. So x equals 0 corresponds to j equals 0. That's one thing. And then x equals 1, which is this one. The index j corresponds to 4. And that's why I have I comma 4 and I comma 0. Okay, so that's one initial condition. We need a boundary condition, which is written here. So the boundary condition is tx0 equals, so let me write it like this. Txj0 equals xj 100xj 1 minus xj. Okay, I just wrote it down, just substitute x with xj. I need to write this in terms of index I and j. So the first index I is time, but the time here is 0. So I write 0. And then j would be the index for positions. That would be j equals 100 xj 1 minus xj. So now I can do is I can cycle over all the j's and write a formula down. So let me move this. Next page. Okay, now let's cycle through all the j's. So we have j equals 0, e0 0 100 0 1 minus 0. That's going to be 0. J equals 1. What I should do is to make it even more clear. Right, x0 is what? 0. X1 is 0.25. So T1j that's the T01, right? So 0 is kept as is, j is 1, so I wrote 1 equals 100 0.25 1 minus 0.25. That comes out to be 18.75. Then we have j equals 2. Here x2 is 0.5. 0 comma j is 2. 100.5 1 minus 0.5. That comes out to be 25. J equals 3. X3 equals 0.75. 0 comma 3. 100.75. 1 minus 0.25 equals 18.75. J equals 4. X4 1. 0 comma 4. 100. X is 1. 1 minus x, so 1 minus 1 is 0. Okay, so in this way, I figured out what is the value for the temperature at time t equals 0, because the first index is time. Okay, now that we've done this, we're now ready to use the two schemes. So first question is use forward time central space. FTCS. Yeah, question. Oh, did I do a mistake? Yes, that's good catch. This should be 7.5. Yeah, my bad. Good catch. Okay, so let's revisit the formula for FTCS. So this is basically going back to the notes. I've summarized all the formulas here. So it's basically this formula which I'll copy. The formula is T I plus 1, comma J equals F T I, comma J plus 1 plus T I J minus 1 plus 1 minus 2 times F T I, comma J. Okay, so now what we do know is that we know the solution for I equals 0. It was written right here. We just need to compute the solution for I equals 1. So let's start with here actually I will be equal to 0. So that I plus 1 would be 1. So T 1, comma J equals F T 0, comma J minus J plus 1 plus T 0, comma J minus 1 plus 1 minus 2F T 0, comma J. Okay, now once we have this formula for I equals 0, we can now start putting in the value for different J's. So we'll put J equals if you put now if you put J equals 0 in this formula, you will not be able to solve for 1, comma 0 because you'll get 0, comma minus 1. There's no minus 1 index. Turns out that you already know the solution for T10. You don't need the formula. Okay, why? How come you know this? If you go back to the boundary condition, so if you look back over here, this is a boundary condition. So it's telling you at when for no matter what the I is, I comma 0 is always equal to 0. So you don't really need the formula. So this is equal to 0, and that comes from boundary condition Ti0 is 0. Okay, so you don't need the formula for the first one. Now, when you put J equals 1, we have T11, that's in this formula. We have F times T0, comma 2 plus T0, comma 0 plus 1 minus 2F T0, comma 1. Okay, now what we need to do is we actually do know the values of all these. F is 0.32, it was computed earlier. 0, comma 2 is available here, 25. 0, comma 0 is available here, it's 0. 1 minus 2 times 0.32. T0, comma 1 is available here, 18.75. Okay, so putting in all those values, you get 14.75. Then we can put J equals 2. We have T1, comma J equals 2. So 2 equals F T 0, comma J is 2. So 2 plus 1, 3 plus T0, comma 2 minus 1 is 1 plus 1 minus 2F times T 0, comma J is 2. So 2. So 0.32, t 0, 3 should be available here. It should be this one, 18.75. 0, 1 is here, 18.75 plus 1 minus 2 times 0.32. 0, 2 is also available here. It's 25. Okay, so doing this calculation, you get 21. You can do it for 3. 0, 4 plus 0, 2 plus 1 minus 2f 0, 3. 0.32, 0, 4. Now 0, 4 is something which is, well, it's here, 0. Then 0, 2 is 25. 1 minus 2 times 0.32. 0, 3 is 18.75. And then j equals 4. Now t1, 4, you cannot use the formula, because if you use the formula for this 1, 4, you'll have to compute j plus 1. So j plus 1 would be 4 plus 1, 5. But there's no fifth index. There's nothing like that, because that's beyond the boundary of the rod. The rod ends at x equals 1, which is j equals 4. So this is actually a boundary condition. If you go back, you can see ti, 4 is 0, where I can take any index. So this would be 0. So this is the boundary condition, ti, 4 equals 0. Okay, so by doing this, we've essentially solved for the temperature profiles at the next time step, where I equals 1 or I equals 1 corresponds to t equals 0.2. Okay, so you'll have to do this for I equals, so this is for I equals 0. We have to now proceed to I equals 1. So let me write that down, and then I'll let you do for the remaining ones at home. So let's do I equals 1. So this will look like this, t2, j equals f times t 1, j plus 1 plus t 1, j minus 1 plus 1 minus 2f t 1, j. Then we start with j equals 0, 2, 0. That's always 0, because the boundary condition is t I 0 is 0. Then we go to j equals 1. That would be t2, 1 equals f 1, 3 plus t1, sorry, this should be 2. J plus 1, so 1 plus 1, 2. 0 plus 1 minus 2f. J is 1. So 0.32. 1, 2 is something you can find over here. T1, 2 is 21. Also, so it's 21. 1, 0, that will be a boundary condition. So it will be 0 plus 1 minus 2 times 0.32. 1, 1, again, here. 1, 1 is 14.75. Okay, that is 12.03. J equals 2, 2, 2, f t1 3 plus t1 1 plus 1 minus 2f t1 2. 0.32 t1 comma 3, we'll get it here. So 1 comma 3 is 14.75. 1 comma 1 I believe is also 14.75. 1 minus 2 times 0.32. t1 comma 2 is 21. So this is 17. Okay, so you just keep doing that. So j equals 3, 2 comma 3. You write it down. The answer is 12.02. It's symmetric, so it will usually have to be the same. 4 is t2 comma 4. Now that will be 0 because there's a boundary condition that ti comma 4 is 0 no matter what the index I is. Okay, so you see what's going on. I'm just computing this for different i's, and then eventually I'm going to just provide this as a table. It's easy to process. So the solution is basically the temperature profile. So what it looks like, well, there would be a time index 0, 0.1, 0.2, 0.3, 0.4, 0.5. But there'll also be a position index. That would be 0, 0.25, 0.5, 0.75, and 1. Okay, so we need to fill this from the calculations you do. This is, since the boundary condition is 0, this will always be 0, 0, 0, 0. And then this is also easy. It's 0, 0. How many zeros do I have? 1, 5, 6, 1, 2, 3, 4, 5, 6. 0.75, 25, 18.75, 14.75, 21, 14.75, 12.03, 17, 12.03, 9.7708, 13.8192, 9.7708, 7.9396, 11.2282, 7.9396, 6.4513, 9.1235, 6.4513. Just happens to be symmetric profile. So you see that 0.5 is the max, and then 0.25 is the same as 0.75, and 0 is the same as 1. Just happens to be. It doesn't have to be this way. Okay. Well, that's the one. That was the easier one. Let's look at the relatively harder scheme. So the other scheme, which I've asked you to use and solve, is the fully implicit scheme. Okay, so let's take that formula and go with that. Okay, so let's look at what the formula looks like. Here is the formula for the implicit scheme. Okay, so I'll just take that and go from there. Formula is minus f T I plus 1 j plus 1 plus 1 plus 2f T I plus 1 j minus f T I plus 1 j minus 1 equals T I j. Yes, it'll just make life easy if I just substitute f here. F is 0.32 and 1 plus 2f will be 1 plus 2 times 0.32. So that will be 1.64, I think. 1.6. So I can just rewrite this because we need it that way. 0.32 Ti plus 1 j plus 1.64 I plus 1 j minus 0.32 I plus 1 j minus 1 equals Ti comma j. Okay, just substitution. That's correct. Yes, so here we go. We plant I equals 0. I equals 0. We also know that Ti 0 sorry, T 0 j equals 100 xj 1 minus xj. So this is a initial condition. It also might help us to note that Ti comma 0 is Ti comma 4 equals 0. This is a boundary condition. So let's proceed and try it. J. Okay, so I cannot take j equals 1 because if I take j equals 1, I'll get 1 minus. Sorry, I cannot take j equals 0. If I take j equals 0, it'll be 0 minus 1. And I really know what j0 corresponds to. It's basically the boundary condition. It's always 0. So no matter what I is, the index j equal to 0 corresponds to a temperature of 0. So I really need to start from j equals 1. So T. Okay, now I'm going to put in I equals 0. So 1, comma 2. So minus 0.32 T. I equals 1. So 1, comma j equals 1. So 2. Subbing in here. Plus 1.64 T1. J is 2. So j is 1. Minus 0.32 T1. J is 1. So 0. Equals T1. J is 1. Oh, sorry. This should be 0. Right? This is y equals 0. Check 1, comma 2, 1, comma 1. Yeah, it's all look like. You know, something I can do here is this term is 0 because that's the boundary condition. I also know what T0 comma I is. So if I want to find 0, 1, I put j equals 1. So it's 100 times x1. X1 would be 0.25. So this would be 100 times 0.25, 1 minus 0.25, which is 18.75. So let me write the new equation. This equation will look like this: 32, 1, 2 plus 1.64, 1, 1 equals 18.75. Okay, so then we put j equals 2 and then rewrite that equation: minus 0.32 t 1, 3 plus 1.64 1, j would be 2, so 2 minus 0.32 t1, j is 2, so j minus 1 will be 2 minus 1 is 1, equals t1, so t0, j is 2. In this equation, I don't know what t13 is, t12 is, or t11 is, because they are at time t equals 1. I have no idea what they are, but I do know what this is. This term is going to be 100 times x j at x2. So x2 is 0.5, 0.5, 1 minus 0.5. This comes out to be 25. So I can now write an equation. That equation will look like this: 0.32 t1, 3 plus 1.64 t1, 2 minus 0.32 t1, 1 equals 25. I'd like to highlight this equation. Okay, so that's one equation which comes out. This is the second equation.
So where do you know that 0, 5 is equal to 100.5?
It's here. Same formula. Looks like this makes it a little bit more clear. Let me do it. This condition is green. Same conditions here. Okay, one more and we are done with this. So let's put j equals 3. So minus 0.32 t. Okay, go back to this formula. I1 j is 3 plus 1 is 4 plus 1.64 t1, j is 3, so 3 minus 0.32 ti plus 1, so that'll be 1, j minus 1, so 2 equals t1, sorry, 0, j, so 0, 3. Now in this formula, what we do know is that t 1, 4 is 0. It comes from the one highlighted in green, that condition. T0, 3 can be rewritten as 100. So xj here, j is 0.75. 1 minus 0.75. Okay, this comes from the thing highlighted in pink. So the math on this will give you 18.75. Okay, so the final formula is 0.32 t1, 3. So t, my bad, this will be 0. So just 1.64, 1, 3 minus 0.32, 1, 2 equals 2.75. We'll pick all these formulas because we'll need them. Second one. Okay, there are three formulas. I'll actually write these down. I think I forgot something. It should be. This is 25, I think. 25 or 21. 25, yeah, 25. Okay, so from this, we're going to write now simultaneous equations. So one unknown is t1, 1. Another unknown is t1, 2. And the third one is t1, 3 equals. So let's write this. So the first one has 1.64. T12 has index minus 0.32. And T13 doesn't appear in the first equation, so that's 0. And we have 18.75 on the right side. Then we have minus 0.32 for T11 here. Then we have 1.64 for T12, and then minus 0.32. Then finally, and this will be of course 25. Finally, we have nothing for T11 in the final equation. Then there's a minus 0.32 for T12, and then 1.64 for T13. And this is, so you see, this is what I was telling. This is an implicit equation. You'll get this simultaneous equation to solve. It's an essential part of using a fully implicit scheme. So if you solve this, you get, so solving, if T11 equals T13 will be 13.0397, and T12 will be, oh my bad, sorry, this is 15.595, and then this will be 21.33. Now, it turns out that once you do this for one, you actually will be able to identify a pattern, and you don't have to really do these calculations, like all these setting up the steps again and again. For example, for I equals 1, we'll get something like this. So you'll have exactly the same form for the A matrix. You would have T21, T22, T23, and then you will have these values appearing now here. So 15.595, 21.33. Okay, so it's just a matter of recognizing the pattern and then solving. So T21 is T23 equals 13.0397, and T22 is 18.0946. Now you need to continue this for I equals 2, 3, 4, and 5. Okay, but you can see that, so not 5, just till 4. But you'll see that it's a pattern. It's not very hard to identify this pattern and then just use it to advantage. So now this will give you another temperature profile, which I'm going to write down as a final solution when you do it for 2, 3, 4. So let's write the solution for the entire I and j swap. So this is the solution. This is the temperature profile. Again, time 0, 0.1, 0.2, 0.3, 0.4, and 0.5. X will be for 0, 0.25, 0.5, 0.75, and 1. So there'll be all zeros for the first time. Six, and then 0.75 and 59, 48, 13.03, 97, 10.9, 366, 9.1889, 7.72, 81, 25, 21.32, and 7, 9, 46, 15.3012, 12.9159, 10.8914. Turns out that 0.75 is symmetric, so it's be the same as the other column. 948, 397, 9366, 9.1889, 7.7. Yeah, and then of course you can compare this with the temperature profile obtained from the fully explicit scheme, FTCS. You see the answers are almost similar.